All right, let's dive into one of the biggest, most profound mysteries in all of modern physics. This is a story about a crime, really, a cosmic crime scene where our two most important theories about how the universe works clash head to head. And what's at stake? Oh, just the nature of information and reality itself. So, think about it like this for a second. If you take a book and burn it, you might think its story is gone for good, right? But according to physics, not really. All that information is just scrambled. It's in the heat, the smoke, the ash. If you were somehow clever enough, you could theoretically put all those pieces back together and read the book again. But what if the fire wasn't a fire? What if it was a black hole? To get to the bottom of this mystery, we have to look at our two main suspects, or in this case, our two main rule books for the universe. And the problem is, when you get to the edge of a black hole, these two rule books give you completely opposite instructions. It's a total contradiction. First up, you've got Einstein's masterpiece, general relativity. This is our best guide to gravity, and it paints a, well, pretty terrifying picture of a black hole. It says there's this boundary, the event horizon, that's a true point of no return. You cross that line and poof, you're gone, wiped from our universe. All the information that made you you is just trapped and lost to us forever. But then we have quantum mechanics. This is the theory that rules the bizarre world of tiny particles. And it has one fundamental, ironclad, absolutely non-negotiable law. You can never destroy information, period. It can be shuffled around, scrambled, hidden, but the universe, it never ever forgets. The info is always there somewhere. So, you see the standoff, right? General relativity says black holes delete information. Quantum mechanics says that's impossible. For a long, long time, physicists could kind of just sweep this under the rug because, hey, who's going to go visit a black hole to check? But then, a massive discovery came along and threw this conflict right in everyone's face. This whole theoretical cold case suddenly became a very, very active investigation, and it was all thanks to one of the most brilliant minds in physics who showed that this wasn't just some abstract argument. No, it was a real, honest-to-goodness paradox that threatened to break physics. So, the year is 1974, and the one and only Stephen Hawking makes a discovery that just completely shakes the foundations of physics. He proved that black holes aren't these perfect, eternal prisons we all imagined. He found out they leak. So how in the world did he figure this out? Well, he mixed quantum mechanics and general relativity right at the black hole's edge. He realized that, thanks to quantum weirdness, little pairs of particles are constantly popping into existence out of nothing. Usually, they just cancel each other out. But right at the event horizon, sometimes one partner falls in and the other escapes. From the outside, it looks like the black hole is actually glowing, spitting out this faint energy. And this leads to the most shocking consequence imaginable. This steady leak of energy, this Hawking radiation, means that over absolutely mind-boggling amounts of time, black holes lose mass. They shrink, they evaporate, and eventually, they disappear entirely in a final little puff of radiation. And boom. Without one incredible realization, the information paradox was officially born. Because, if the prison itself eventually vanishes, you have to ask a pretty serious question about all the prisoners that were trapped inside. Where does all that information go? What happened to the history of the star that made the black hole? What about that poor astronaut who fell in? Is all of that detail, that story, is it just completely erased from the universe forever? Now, here's the absolute killer detail. Hawking's original math showed that the radiation coming out was completely random. It was thermal, which is just a fancy way of saying it's a featureless hiss of static. It contains zero information about what had fallen in, and that would mean the information is truly, irrevocably lost, a total violation of quantum mechanics. Physics was officially broken. Okay, so how do you solve a crime that seems to break the fundamental laws of the cosmos? Well, you call in the world's best detectives, in this case, theoretical physicists. And they have cooked up some of the most brilliant and, frankly, wildest theories you can imagine. I mean, the proposed solutions sound like they're straight out of science fiction. You have things like the holographic principle, which suggests all the information isn't lost inside at all, but is actually perfectly preserved, sort of painted on the event horizon. Then there's the firewall hypothesis, which is even crazier. It suggests that anyone trying to cross the horizon gets instantly incinerated by a wall of fire. I mean, each of these ideas totally stretches our sense of reality to the absolute breaking point. For the longest time, these were all just fascinating ideas. But very recently, a major clue has surfaced in this cosmic investigation, and it's given physicists real hope that quantum mechanics might just win this fight after all. It's called the Page Curve, and it basically predicts the life story of the information. It says that as the black hole evaporates, the escaping radiation gets more and more random, more disordered. But then, and this is the key, right at the halfway point of the black hole's life, something amazing happens. The trend flips. The radiation starts to become less random as it slowly but surely starts carrying all that hidden information back out into the universe. And here's the most exciting part. Just in the last few years, a bunch of incredibly complex new calculations have basically confirmed that the Page Curve is correct. This is a huge deal. It's powerful evidence that information is preserved. It really does get out. We still don't know the exact escape plan, but now we have a mathematical map telling us where to look. Now, you might be thinking, this is all very cool, but it's super abstract. Why should we spend so much time and brain power on this one cosmic puzzle? Well, the answer is that solving it could unlock the deepest secrets of the universe. See, this isn't really just about black holes. It's about finding the holy grail of physics, a single, unified theory of quantum gravity, a theory that finally connects Einstein's world of big things, like planets and galaxies, with the quantum world of tiny particles. Black holes are the one place where these two theories are forced to talk to each other, and this paradox is the ultimate test that any new theory has to pass. So solving this paradox won't just tell us something neat about black holes. It could completely rewrite our understanding of space, time, and reality itself. It makes us ask what information even is and how the universe keeps its records. Which brings me to one last, completely mind-bending thought inspired by one of the leading solutions. What if this whole paradox is just a giant clue, telling us that our three-dimensional reality is some kind of illusion? That all the information that makes up you and me and this entire universe is actually written on a distant two-dimensional surface at the edge of everything, kind of like a cosmic hologram. Something to think about.